My team and I are here today to present you progress about using autonomous robots at any time and in any environment, however strenuous and demanding this might be. We call this, as from the title, robot autonomy in the wild. We believe that such robots can be used to probe and explore extreme natural habitats, such as underground caves or glaciers, where we are actually located in Norway. And likewise, also be used to monitor, inspect, and maintain critical infrastructure and industrial facilities at the best possible standing, therefore also reducing their potential environmental impact. But we ask ourselves scientifically, what is a common way that can allow diverse robotic configurations, walking systems, flying systems, or even swimming systems that you will not see today because making a pool will be very difficult, to operate with resilience in any environment under extreme conditions? Before we go ahead to discuss technology for the same, we are going to do a small demonstration here on stage. You're going to see two robots, a legged robot and a drone, but they're going to be working together in a marsupial fashion. So the drone is sitting on the back of the quadruped. And they will be tasked to explore this area we have built here on stage, which involves two compartments. One you can see through, and it has a net, and one you cannot see through. The two compartments are connected through a small access hatch. And the key is that the quadruped does not fit to go through this access hatch, right? So it has to rely on the drone. So with that, the word is on my team, which are ready to do the demo for you. So now the quadruped enters inside. And as I told you, there is a small access hatch. Possibly you see it from the video. And it cannot go through on its own. So it will depend on the drone to explore the remaining of the environment. Of course, we are doing a demo here on public stage, so everything is enclosed with nets. We're going to close the door, some safety precautions because you are here, and we don't want to create accidentally any issue. Having said that now, the robots, to operate in their mission, they rely on their onboard sensors. So the onboard sensors involve a set of different modalities, laser scanners, could be radars, accelerometers, gyroscopes, vision systems, and so on and so forth. And as you already saw, the quadruped now has opened its extra structure on top to allow the drone to be released. Give us now some time, because sensors take some time to wake up and get ready for operation. Yep. So next step. Once it enters, you will see the data. Can you show Arvis? Yeah. And now you see the 3D model of the system as it reconstructs the environment and the paths from its navigation. So this demo is small, because this is a small environment that we have built, but we haven't stopped yet what we want to show. So now, Mihir will be moving the screen of the 3D data from the robot, and you see the small compartment it has built, but also, Mihir, if you can please show further away for the overall room. And yeah, so we will increase a little bit the size for you to have something a bit more visible. Yeah, so I don't know how visible it is from there, but this is actually the room we are all sitting. So it's important to highlight some few things in this small demonstration here on stage, that we did have a safety pilot, but the safety pilot was not there to intervene with the robot unless necessary. Nothing happened bad, so the safety pilot was only there just for the sake of being around. And the second important thing is that we indeed built this facility, but we do not provide information to the machines about the environment they are tasked to explore. So let me now come and ask the question, what it takes not to do this demonstration here on stage for the sake of presenting to you the capabilities of robotic systems in principle. What does it take to use robots in extreme conditions seamlessly, without any worry, without a team behind the robots to make a demonstration? To understand the challenges, we can look at a well-known paradox in the field, both of robotics and AI, Moravec's paradox, which states elegantly that typically what is hard for humans, for example, doing complex mathematical calculations, is very easy for AI, or tends to be very easy for robots. And likewise, on the other way around, what is very easy for humans, maneuvering around any complex environment, using your hands in a dexterous manner, tends to be still very difficult for robotic systems. And this is a paradox that is known for decades, not something new. And we can only relate to some examples. For example, we can see a toddler, and the toddler one day learns to walk, and seamlessly afterwards, very soon, maneuvers any place in the world with robustness. They may fall, but they can still manage to continue. Or a baby one day learns to understand that this is a cat, and then the next day you show a sketch that you just draw yourself, a terrible sketch, and the baby still understands that this is still a cat, so we generalize very well. And later in life, not when babies, we understand very well the notion of risk. So when we are going around something we can actually not do safely, we don't do it. We remain safe, so we have a good understanding of the model of what we can do in the world and what we cannot do. Unfortunately, or good for us as researchers, robotics are not there yet, and we have to find a way to get the same capabilities. So we humans and other natural beings are very resourceful. We have redundancies, we deal with disturbances, we handle uncertainty, we generalize from previous experiences to new experiences, and we find our way to do what we want to do, even in the presence of adversity. Robots are not there yet, and we question ourselves how we can actually bring them to this level of resilience, such that robots are not there in a demonstration, but everywhere around us, and they can execute something useful for the society. My team and I, we are working to instill resilience across the robot stack. So from how a robot sees, with camera sensors, laser scanners, radars, different sensing modalities, how the robot fuses the data that it sees to understand the world and reason about the world, about what it can do in this world or what is inside this environment. And then how a robot can plan its actions to execute something useful, safe for itself, safe for its surroundings, and of high utility for the humanity. And last, of course, how a robot can actually deliver its actions. Can it actually move and execute what it needs to be? And it's important to highlight, because this is robotics, and it's not only a software system. It's not only about the intelligence, as we think of it as humans, that we take for granted most of the times our body. Body is very important for robotics. So, for example, you see some videos that the drone collides and sustains. It's a soft system. And by being soft, much like insects, can collide and can get more damage without it actually having to stop. So, I don't like hype, and I don't want to say that robots are there yet, and they are not. But we can pull already several feats that I hope you can find impressive. So these are some results from the group. For example, a drone that navigates inside dense smoke and maneuvers the world with fusion of LiDAR and radar sensors and goes in areas we could even be challenged to navigate. Or a quadruped that operates completely autonomously for several kilometers of navigation to explore an underground mine and come back with a map without the need for a human to enter this dangerous and difficult environment. A soft drone, as mentioned before, that can sustain trouble and damage and can fit through cross-sections more narrow than itself. There is a very good video from BBC with a bird that does something like this, way better, of course, and we are motivated from what we see in nature. And robots that have no prior information for the scene, much like this little demo, but not only in this little small stage, and enter unknown areas and come back with high-detailed 3D models, not only geometrically, but also we reason what we see in the world. And this is for free. Robots can do this in a very efficient manner. For free, I don't mean cost-wise. I mean without the humans being there or the humans having to teleoperate. We are talking for systems without any need for teleoperation or commanding, purely autonomous machines. And having said that, subject to the fact that we slowly instill these capabilities to robotic systems, we can go ahead and do useful missions. So I will just organize over two types of activities, natural environments and industrial environments. So we have been in extreme natural habitats, in the Moaning Caverns in California, mapping the cave system. Or in the DARPA Subterranean Challenge, together with other partners in a team we led, we had the opportunity to explore simultaneously caves, mines, subway infrastructure, and so on and so forth. Or, for example, fly under the canopy of forests and observe the differences that are impacted from processes in the climate and the nature in general. Or on the industrial front, we can monitor critical infrastructure. What you see in the videos on the bottom level is ballast tanks of a ship or a nuclear power plant in the United States or an underground mine. So we have some progress, And I think we can continue this direction, and not necessarily tomorrow, but soon, robots will be able to operate in the wild. And we also have identified, we believe, 2 critical directions that we can put our efforts. The first is that the same robots are used pretty much all the time. They either look like miniature manned aviation systems or manned systems in general, or mimicking nature. But actually, we can do not only mimicking, we can do the idea of nature, of specializing robots to a certain ecological niche, meaning robots that are evolved and trained to be best in a certain environment. So, for example, a class of environments, forests, and so on and so forth. We call this computational co-design of the robot body and the brain, and we have some progress in this field. And second, beyond core research, we can also do right now robots that are useful for the society, either to inspect infrastructure or, for example, even more bold goals, using autonomous systems that can help suppressing wildfires with their own capacities. So with that, I want to actually give you the final message that resilience is key. Resilient autonomy is very hard to achieve, but also an exciting endeavor for us to manage. And second thing I want to say, I want to credit our sponsors, the public sector, that is there to support this fundamental research before it actually pans out as an excellent result we can see in a video. My team, that we're here to do the demonstration for you, so Marvin, Jorgen, Mihir Damardikari, Mihir Kulkarni, that spend a lot of time shipping robots from Norway, coming to Switzerland, just to do the demonstration for you. And of course, some credit to our robots, the drone built at the lab, and the animal-legged robot that was from a company here in Switzerland, Robotics, modified to carry our drone. So with that, I want to thank you and give the stage. Thanks a lot.